Welcome back to the Chem OG. Today we're going to take a look at a specific class of biomolecules called triglycerides. Triglycerides are compounds that contain 3 ester functional groups. And so these molecules are fat-soluble. They're not particularly water-soluble. So when I refer to the 3 ester functional groups, I'm looking at this ester, I'm looking at this ester, and I'm looking at that ester. And all of those esters are connected together through one common carbon backbone that contains 3 carbons. So that's where the term triglycerides come from, is that you have a carbon backbone that contains 3 carbons. Now, triglycerides are also called triacylglycerols. Sometimes they're also called triacylglycerides. And they're in fact how our bodies store sugars. So when we have sugars and we metabolize them, we store them as fats in the form of triglycerides. Now, triglycerides are composed of that carbon backbone, like I told you, and they're also composed of fatty acids. So if we kind of break things apart here and yank the 2 big parts of our molecule together, the part on the left, that 3-carbon backbone, is called glycerol. And the part on the right, and there are 3 different ones, they're called fatty acids. Now, those fatty acids could all be the same. They could be 2 of the same and one's different. Here, just for the sake of an example, I put 3 different fatty acids down. Now, these are called fatty acids because they contain a carboxylic acid, and fatty because they contain a long carbon chain on each of those. Now, in order to break that molecule apart, implicitly what I had to do was I had to put in an extra oxygen, right? Because this oxygen over here and this carbonyl oxygen over here were initially connected together. And so in order to be able to separate the glycerol from the fatty acids, what I had to do is I had to insert an extra oxygen. And so breaking up these triglycerides requires an oxynucleophile. And you have to have an oxynucleophile for each of those 3 esters. So if I have sort of the generic form of a triglyceride with different R groups attached to my carbonyl to fit at each of those esters, what I would need to do is I would need to get an oxygen in order to break these guys up and transform my glycerol by itself and to have the fatty acids by themselves as well. So I would need to have an oxynucleophile in order to break these guys up. Now, one such reaction that could help us to break up that triglyceride is a reaction called saponification. Now, it's called saponification, and it takes its name from soap. And the reason that soap is invoked here is because, especially old school soaps were composed of lye or just plain old base. And so saponification is a reaction that occurs in the presence of hydroxide, and it happens through an addition-elimination mechanism. So let's take a look at our triacylglyceride once again. Remember, we had to have an oxynucleophile, and so hydroxide here is going to serve as our oxynucleophile. And at each one of those carbonyl carbons, the hydroxide is going to attack that carbonyl carbon. And what's going to happen after that is our electron density is going to move up to the oxygen. So remember, when a pi bond disappears, that's called an addition. And then we're also going to have this oxygen come back down, or those pi electrons come back down, and they're going to reform the pi bond, and that's an elimination step. And so all of this particular type of reaction is known as an addition-elimination reaction, and that's something that we explored in our acyl substitution video from before. So you can find a link up at the top right in order to be able to access that video. And so hydroxide is going to come in and is essentially going to kick out these esters, and it's going to liberate them as carboxylates. Now, notice that the oxygen that's left behind on our glycerol backbone is the oxygen that attacked as a nucleophile. So I've kind of color-coded it here as blue. And the oxygens that left, those are oxygens that are now contained in these carboxylate functional groups. So every now and again, depending on what exam you're taking, radial labeling kind of features prominently in terms of the breakup of these molecules. So the nucleophile that came in is going to stick around with the glycerol, and both of the oxygens that used to be on the ester are going to be with the conjugate base of these fatty acids or these carboxylates. Now those carboxylates in the product are now water soluble. And so the purpose behind this reaction in terms of a saponification or ones that we digestively go through that are similar to saponification is to convert these fats into something that our body can be able to deal with, and that's water soluble. In fact, this particular reaction in terms of reacting with a fat through a basic environment and converting it into something that is water soluble is something that happens in our duodenum, in our small intestine. And so the purpose behind breaking up that fat is to be able to convert it to something that's water soluble that our body can use as a metabolite. Thank you so much for watching today's video. Please be sure to support this channel by hitting the like button. And if you haven't done so yet, please be sure to subscribe. See you next time.